Welcome Mechanics of Materials students. This is our fourth lecture on the subject of beams, and in our previous lecture we derived the Flexure formula, which is an expression that relates longitudinal stress or normal stress in the x direction, meaning the direction along the beam or parallel to the beam axis, as a function of the internal moment at that position, the cross-section moment of inertia with respect to the z-axis going through the centroid of that cross-section, and the distance above the neutral axis of the beam, meaning towards the center of curvature. Okay, one thing that we did mention in passing was the potential effect of a direct applied axial stretch, as opposed to the forces and stresses that come from flexing the beam. So we can either grab a beam and just stretch it, or we can keep the end supports of the same distance and just flex it. So we have that would correspond to our N, capital N, internal force, meaning a normal force, normal to our cross section, or M, the flexion. So we're going to take a little bit of look at the relationship between the axial or longitudinal stress due to a stretch and the axial stress due to flexion, and the position of the neutral axis relative to the centroid of that cross section. So to do that, we're going to go back and we're going to do a little mathematical wrangling with the definitions of normal force on a cross section, normal stress or stress in the x direction, longitudinal stress, and then the longitudinal stress from bending that we just defined. So if you remember from early in our discussions of beams and normal forces versus stresses, normal to a cut face going in the x direction along a beam, we can define the normal force on some cut section as the integral of the stress in the x direction, or the stress in the direction normal to that cut face, integrated all over the area. Now we also just derived an expression for that sigma xx, if it happens to be due to bending, isn't going to be uniform over that area, and in fact will take this form, which is what we just derived from the Flexure formula. But it is a sigma xx, and if we plopped it in to this integral in place of sigma xx, if we wanted to define a normal force, it would give us a normal force. Depending on how much of the area we integrated over, it would give us the entire normal force due to that flexion or not. Now, if you think about a uniform symmetric beam, you might conclude that if the same area of beam was above and below the neutral axis, then this integral might end up being zero. It all depends on, whether or not enough of that area is above or below. So let's think about that a little bit. If we look at this integral for any x position along the beam, because remember we're integrating the area of the cross section, and that cross section is being taken at a given x location along the beam. Let's say for any x position along the beam, moments constant, and let's assume we have a uniform cross section everywhere on the beam, and so of course, and even if it weren't at any given x location, our IZZ is going to be constant. So we can pull those out of the integral. So we can say the normal force or axial force at any given x location is going to be negative moment at that location, internal moment, divided by the moment of inertia times the integral of y, which is the distance from, again, defined back in our Flexure formula, the distance from the neutral axis to some point of interest with respect to area over the cross section. We can take a look at this expression and say, well, another way of expressing that is the centroid position times the cross section area, and because centroid is now referenced to this y value, which was itself defined in terms of the neutral axis via the definition of the Flexure formula, this y bar is the y centroid location reference to the neutral axis y position. So we're used to thinking of the centroid being defined as some geometric location, and then we could say, okay, is the neutral axis above or below the centroid? The point of view of this particular expression right here is we know the neutral axis is somewhere, and it's defined geometrically, but also from a stress-strain standpoint as the one spot that doesn't change length. It may or may not correspond to the actual centroid of the cross section. And what this formula says is this y bar is the centroid location relative to the neutral axis. And then of course A is just the actual cross section area. So what this is saying is if you're flexing a beam and you're applying moment or shear, but you don't stretch the beam at all. You're not applying any direct axial loading. So our n at whatever x we care about is 0. Maybe we've already canceled it out. We've put it in equilibrium. Then n at that x location is 0. That means this whole expression is 0, which means this product of what's in these parentheses and these parentheses has to be 0. Well, this first term is not 0 because the cross section has area, and if it has area, it has a moment of inertia. It presumably has a moment, or we wouldn't even be discussing flexure, which means the term that is probably 0 is this one. So if the y distance between the centroid of that cross section and the neutral axis is 0, that means the centroid is on the neutral axis. So there's no distance between them. They're the same point. So another way of saying this is in the absence of axial loads. So if we're not compressing the beam or stretching the beam and we're flexing it, then the neutral axis will pass right through the y centroid of the beam cross section. If we're stretching the beam or compressing the beam, then there's going to be some distance between the neutral axis and the centroid. So the neutral axis will be above or below the centroid, and the distance above or below will be proportional to the actual magnitude of that axial force times these other three terms. So the neutral axis won't always be on the centroid, but if the axial forces are insignificant really compared to the others, we can probably assume it is. So we'll get to a few examples as we go on where we compare those two. But I've done this little breakout, this mathematical breakout, just to show the relationship between axial force and the distance between centroid and the neutral axis. The neutral axis is not always on the centroid. And what determines whether or not it is whether or not we've got a stretch or a squish axially in addition to our flex. Okay, speaking of flex, we've only considered flexion m sub z, so we're rotating that cross section around the z-axis. You know, we've got a beam, we can twist it or we can flex it in multiple different directions. We can flex it kind of vertically, and we can flex it in the horizontal plane as well, in addition, of course, to twisting it torsionally. We're not considering torsion. But we have a whole other axis we can flex it around. And if we flexed it in that axis, presumably we could get some additional tensile stresses somewhere. So let's explore how likely that is and whether or not that's something we need to consider. So we could define moment about the y-axis as being the normal stress on some little area here times the z offset, because the z is now going to define a radius. So we're going to basically be, creating a moment about the y-axis in that case. So we could define that, and because of that we would end up inducing a sigma zz stretch due to some horizontal flexure, a horizontal moment, applied moment. So we could look at that and see whether or not that's going to be something we have to worry about depending on the beam shape. So let's just apply sigma xx due to a horizontal applied moment using our flexure formula. IZZ m sub y. So if we continue our math through, we end up with our applied moment in the z over izz, and now instead of like a y squared, we have a yz dA. This is a product of inertia in the yz plane. Lucky for us, if either the y-axis or the z-axis is an axis of symmetry, then products of inertia go to 0. And if the product of inertia goes to 0, then we're not going to end up having any like induced moment m sub y due to axial forces. So if you've got a symmetric beam and you're only bending it in the xy plane, you're not going to get any internal moments about the y-axis. If you actually applied a horizontal moment, then you could use this expression to create another little flexure formula and have like a horizontal neutral axis. But if the beam is symmetric and we're only flexing it in the xy, then we're not going to have to worry about induced moments about the y-axis. We're going to only have to worry about our induced moment or about the z-axis, which is the one that we typically calculate for a 2D beam. This condition of geometric symmetry that allows us to bring this product of inertia to 0 is that characteristic is known as a symmetric beam or symmetric cross-section. So if you see chapters in the textbook or descriptions of beam analysis of symmetric beams, this is what they're talking about. If you had something that wasn't symmetric, where your stress sigma xx could induce a moment about the y-axis, then you would have to worry about that other product. We will only be concerning ourselves with symmetric beams, so basically our m sub z, our internal moment in a 2D beam, is the only thing that we're going to be worried about. Our induced flexure, our izz, about our symmetric cross-section. But the other does exist, so non-symmetric beams are out there. So be aware that will be an additional factor you might have. So let's do a quick example, actually not so quick, but a great example, applying the flexure formula. So we have a symmetric beam. Here's a nice cross-section. So here's our y-axis and our z-axis going right through the centroid. The beam is extending out towards us through the screen. It's 80 millimeters in height, 30 millimeters across the base, 15 across the top surface. And we're told it has a maximum internal moment of 7,956 Newton meters. So somebody has already analyzed the beam with its loading and said, okay, the maximum moment, wherever it happens to be, at whatever x, this is as big as it gets. So this is a point we're going to analyze around. This is the bounding case in terms of worst x position. We got a material, which means we've got a yield stress and maybe some fracture information. So that's going to give us our upper limit for sigma xx. Apply whatever safety factor. So we kind of have a point in the sand there. We got our cross section. So that cross section is going to give us two things important for the flexure formula. One, if we are not stretching or compressing it and we're only flexing it, then this centroid is the position of the neutral axis. So we immediately know that if we're flexing it upward, and this is the bottom of the beam, this point here would represent the maximum tensile spot. So all we'd need to know is this y, and that would be the y we would use in the flexure formula. If we had an applied normal force stretching or compressing the beam, then the neutral axis would float upwards or downwards from that centroid, and we would use the distance from the neutral axis for our max. And we can use all the other dimensions to get our izz, which is actually the most complicated part of the problem. So first we're gonna locate our centroid using the method of composite areas. So we're going to use two triangles and a rectangle, so we can get our centroid of the rectangle and our area of the rectangle, and our centroid. We only care about y centroid. Obviously the z centroid, it doesn't factor into the problem. It is at z equals 0. We know our y centroid of the triangle is 1/3 of the way from the base. We don't have to integrate for that. So we know that our y centroid of the total area is times the total area is equal to the y centroid of each part times the area of the parts. So our y1 y1 bar, our centroid location of the rectangle times the rectangle area is area 1, plus 2 times the y centroid location of the triangle times the triangle area. We got two triangles kind of flanking the rectangle. Cut it there. You know, so those are supposed to be vertical. So we add that up, and we can calculate these two kind of by observation. Area of the rectangle is 15 millimeters times 80 millimeters. Area of the triangle is 80 millimeters times 7.5 millimeters divided by 2. And divide by the total area, so we get a y centroid of 35.35. So a little below the halfway point is going to be our centroid. So having calculated that, then we need our IZZ, our moment of inertia. We can use some tables. There's probably some tables in the back of just about any textbook you might be using. If you're using a table of moments of inertia, in most cases, different values will be listed for an axis through the centroid versus an axis across the base. And if it's not a totally symmetric type of shape, there'll be, there'll be a different moment for rotation along different axes. And then a polar was, of course, the sum of the two orthogonals. So in this case, IZZ1 of the rectangle, we're going to look across the base here because we're adding up the base, we're adding up moments of inertia of two different shapes, each of which have a different centroid. So we're going to add up across the common centroid, get a single moment of inertia, and then we're going to kind of use the reverse parallel axis formula to shift that up to the composite centroid. So we're going to pick the centroid of a rectangle along its base, which is 1/3 of the base times the height cubed. If this had been through the centroid, that'd be 1/12, so this is a lot bigger. And then for a triangle, it's 1/12 base times height cubed, so we can get a value for each of these. We add composite moment of inertias just by adding the moments of inertia. So the total shape is going to be the moment of inertia for the total shape is the moment of inertia for the rectangle plus 2 times the moment of inertia for the triangles. And so we get a composite number. Now we reverse out the parallel axis formula to get our IZZ around the centroid, which is what we need for the flexure formula, because we're rotating about that centroid or the neutral axis, which is the centroid in this case, when we got a flex. That's what we're rotating around. Each of those cross sections is rotating about its neutral axis centroid. So we use our IZZ of around our base minus the total area times the distance between the base and the centroid, which we know from up here. And so here's our IZZ. So okay, we've got our centroid distance from what's actually going to be our maximum tensile axis. We've got our IZZ. We were given our maximum moment. We should be all ready to calculate. So we can calculate the max compressive axial or longitudinal stress at the top surface. So we've got a little bit more distance to the top. It's positive. So remember, the flexure formula has a negative out front, and so we have traveled a positive distance towards the center of curvature to get to that compressive axis. So we're looking at that surface is the max compressive surface, max moment, moment of inertia. So negative 384 megapascals, not insignificant. Max tensile, we're going to go down 35.56 times 10 to the minus 3 meters, which is our centroid distance. We're going to go down, so that's a negative. We got a negative out here, so we end up with a positive sigma xx, which indicates tension, and it is thankfully a little bit less. So that tells us something about which way we'd rather flex this cross section. Where are you going to, if you want to limit max tensile stress, do you want to orient it such that the broad end is on the bottom or the broad end is on the top? If you are designing a beam that limits tensile stresses, you're going to want to put that broad end on the bottom because that pulls your, in the absence of stretching and compressing, just flexion, your neutral axis is your centroid. Your centroid is closer to your max tensile surface. That means that y value is less. So we've got and it's a linear relationship, but hey, you got the same beam, you can put it in upside down or right side up. So basically you saved, 72 megapascals out of about 400. That's not insignificant, especially if you need all the safety factor you can get. Okay, so let's look at moving that neutral axis. Let's apply an axial tensile load. So let's actually stretch the beam. It's a little bit harder than compressing it. If we wanted to compress it, all we'd have to do is constrain it and heat it up. But let's assume something is happening, that it's actually being stretched somehow. But it's also being flexed. So we have that max moment of the 7,956, but we also have an N, so an axial force of 1,541. So we're going to go back to that expression that we used where we plopped in the sigma xx integral over area equaling the flexural sigma xx, because basically the stress is going to be the result of both forces. We got the same moment, and we're going to take a look at what's going on along the beam. So we put 1541 in for our axial load, not an axial stress, axial load, and that's going to be equal to basically our flexure component with this time instead of y being the distance from the centroid to our maximum tensile axis, now we're looking at the centroid to neutral axis and then the cross-section area. So if we're going to do this for our sort of trapezoidal figure, we end up with a total cross-section area of 1.8 times 10 to the minus 3 square meters. Same moment of inertia we had. We know our applied moment. This is negative. We were told here's the axial force, so we can solve for, hey, how far did the neutral axis shift from the centroid in order for the rest of this expression to be true? So we can basically go through this. First of all, we can look at the stress that would be due to that axial load. So we can take n sub x and divide by the cross-section area, solve for a value. So that's another way to express stress. We know that the whole axial load is 1541. If that were uniform over the whole cross-section area of 1.8 times 10 to the minus 3, it's less than 1 megapascal. The maximum tensile loading from flexion was 308. So we've got 1,500 newtons of stretch. We got 8,000 newtons, so about 8 times the moment. But the axial force, or excuse me, the axial stress due to that flexion at its maximum point, down on that max tensile surface, is significantly more than the stress due to the axial load. So the first conclusion we can make is that even a fairly significant force stretching this beam ends up resulting in a fairly small axial stress compared to what we can get at that maximum longitudinal stress point from flexure. So you want to put something into some significant tensile stress, flexure will get you there faster than just outright stretching it. Okay, let's see what happened to our neutral axis. If we manipulate this, we know what the cross-section area is, we've been given what the actual axial stress is, or excuse me, axial force is. Let's solve for this term. So we have this down here. So we've isolated the y-centroid to neutral axis distance, solving for that, and we get a negative 9.9 times 10 to the minus 5 meters. So a little less than 0.1 millimeters, and it's negative, so that means from the centroid to the neutral axis is negative. So effectively, that distance means we basically dropped the neutral axis down. So if you go from the centroid's not going to change. It is what it is. It's based on geometry. But now, rather than going through the centroid, the neutral axis is a bit lower. So the new neutral axis is just a titch below where it was before. So not by much. Now, if you look at the magnitude of this axial force, if this were, say, 15,000, this would be 10 times bigger, so it would be maybe 1 millimeter. But still, the entire height of this, remember, was 80, so it's still not dropping very much. So you will get a change in the neutral axis when you apply axial loads, but they have to be pretty big, generally speaking. Of course, if you have a lot of stretch and you have a very small beam, very small height, that might be something you need to look at. This is something that you will see more when you have composite beams, either a fiber polymer composite or a reinforced concrete beam. A lot of times you'll need to take into account exactly where the neutral axis is. Has it shifted up or down when you're looking at where to put your tensile reinforcement? Because as you can probably guess, if you're looking at a big beam in flexion, a lot of materials cannot tolerate tension, and so you'll be using a composite where one of your components of your composite is very capable of supporting tension, and so you're going to want to put all of that pretty close to where your max tensile axis is. So knowing where your neutral axis is and inferring where your max tensile axis is helps you space out your tensile reinforcement when you need to. And that's particularly important for concrete, because in that particular composite structure, you have your concrete matrix, which really can't support any tension. Polymers with fiber reinforcement tend to be a little more tolerant. Okay, that is it for longitudinal stresses. So just to recap, we've taken a beam that's straight, we put a grid on it, we've looked at the geometry of flexion, we've looked at radii of curvature and distances between points, and we've related that to an axial strain, sigma xx. We've looked at Hooke's law and related that axial strain to an axial stress, sigma xx, and then we've gone back to the definition of moment for flexion about the z-axis through the cross-section of a beam and related our sigma xx to moment that we can solve from a statics problem. And from that we derive the flexure formula. Then we did an add-on and said, hey, what if I have a bit of combined loading? I'm flexing and applying a moment, and maybe I'm stretching or compressing as well. And we looked at relative magnitudes for sigma xx from flexion versus sigma xx from just an outright stretching or compressing, and then the shift of the neutral axis relative to the centroid if we had that combination of loading. So the next topic we're going to dive into in the next lecture is deflection. So we talked about the beam flexing, we've turned something straight into something curved. How curved did it get? And how far did one end go up? And what if I didn't want it to get very high? So we're going to turn our attention from what's effectively a stress limited design to a deflection limited design. So we may have a beam that's really, really capable of supporting quite a bit of stress, but depending on its modulus, it may move a lot. And so we may have a design that's limited by it moves too much, and so we may have to adjust other things to meet two requirements. So we'll dive into that in the next lecture.